Hello, everyone. Welcome to Introduction to Semiconductor Devices. I'm Naresh Imani. I'm a faculty member in the Department of Electrical Engineering at IIT Hyderabad. It's my privilege to offer this course on the NPTEL platform. This course aims to develop the foundations of semiconductor devices, and we hope that it is useful for various other courses that you might be interested in the future. For example, courses in VLSI design or in embedded programming or in power electronics and so on. So we will try to develop the broad foundations of semiconductor devices. And why should we be interested in this course? Well, if you look at the modern life, we are all surrounded by semiconductor devices. We see, semiconductors in our cell phones, in our computers, and I mean, literally everything around, every gadget around us has semiconductor devices. So if you look back in the last 75 years or so, I believe that there have been two significant inventions that have changed the modern life. The first one was a MOSFET, which is essentially what you see in your cell phones and all that, right? It's the heart of it, these devices. The other great invention has been the invention of a semiconductor laser. So, semiconductor laser has essentially made it possible to have long distance fiber optic communication. That is also, built out of a semiconductor. So basically, these two have been some great inventions. And of course, we have many system level implementations. For example, in autonomous navigations nowadays, that's becoming very important. And these systems are actually, there are many computers present within an autonomous car, or you have the autopilot systems that's been around for some time in the airplanes. These are again system level implementations which are actually making the modern life more efficient and secure. So it's really inconceivable to think of a life without semiconductor devices. So we would like to understand some of the basic aspects of semiconductor devices and how they work. And the journey into understanding this, we should go back to the roots. So this computing revolution, or information technology revolution, started in, I would say, in about 1940s. During the World War, people realized that there is a need for computers which can calculate very fast and efficiently. And one of the milestone devices was called ENIAC. It's an abbreviation for Electronic Numerical Integrator and Calculator. I'm showing you a picture of ENIAC here. So ENIAC was made up of vacuum tubes. Vacuum tubes were the predecessors of the modern MOSFETs. They were glass tubes with, of course, vacuum in them, and there are some electrodes, and you pass current, and then you can show transistor-like action. These were bulky, very less. I mean, they had less reliability, and they were very expensive. So it was not an efficient device, but that's what they could build in the first iteration. And you see a picture here, ENIAC, where you had vacuum tubes which are connected through wires. And there are also two scientists who are actually programming devices. So that gives you a length, the size scale of these devices. They were essentially encompassing an entire building for one computer, right? So immediately scientists realized that there is a need for a solid state alternative to a vacuum tube. And this quest ended in the year 1948 when at Bell Labs, a team consisting of Bardeen, Brettain, and Shockley, they invented what is called as a point contact transistor. It was a very crude device, but it showed semiconductor transistor-like action, and that's why it was a revolutionary breakthrough. And Shockley, Bardeen, and Brettain got a Nobel Prize in 1956 for this invention. So after that, in the next 2 decades, there have been very significant breakthroughs that enabled the fabrication and design of MOSFETs. And finally, they managed to integrate MOSFETs on a single chip. So instead of having single individual transistors, scientists managed to integrate them on a chip. And that was the genesis of the modern integrated circuit, or IC. And in the next 40 to 50 years, there has been exponential increase in the number of transistors that are packed onto a single chip. So much so that today we have our Xeon processors, or maybe Core i9 processors and so on, the latest and the greatest processors, which have billions of transistors which are packed into an area of about few square centimeters. So very tiny devices, but they pack enormous computational capability. There are thousands of times better than the old ENIAC systems. So this has been a great journey. And this journey has been famously captured by Gordon Moore, who was the chairman of Intel. And then he said in the year 1960, 65, I believe, around 65, he said that the number of transistors on a chip doubles every 2 years. This is an empirical observation. It had no scientific basis. He just saw a trend and he said, okay, this is the trend that, it's interesting and it should keep up. And this sort of became a holy grail for the semiconductor industry. And companies started trying to race against this, and they started building more and more efficient semiconductor chips. And that is what is shown in the graph here, which captures Moore's law. So on the x-axis you have the years, starting from 1900s to the current times, 2021. So how does the computation capability scale? So on the x-axis you have the time, and on the y-axis we have calculations per second per $1,000. So essentially what we're trying to say is how many calculations, how fast is a chip, and how cheap is a chip. If either of these parameters, if it becomes faster or cheaper, the y-axis will grow, right? So you see that over the last 50 to 80 years, there's been a great increase in the computational capability, and an exponential increase rather, because you see on the y-axis, it's a logarithmic scale. So you have an exponential increase in the computational capability over the last 70 years. So if you look at in the year 1940s or mid 40s, only one or two calculations per second per $1,000. So it was very, very expensive to perform calculations. But there's been growth, exponential growth after that. And you see the famous, Pentiums and all that, which were, when I was growing up, these were the main processors. And of course, now you have quad i7, of course, i9 and so on. It's still going on. But, there are some challenges to Moore's law right now. And it's a very interesting research problem nowadays that, what next? If what will be the future? So there are many proposals, optical computing, quantum computing, and DNA-based devices, and so on, or biological inspired devices. So there's been a lot of research there is a lot of research going on, and no one really knows what would work, but it's a fertile research domain, okay, which has very significant implications to our life. So in this course, I want to develop the foundations for understanding semiconductor devices. So my effort would be to develop the basic principles, try to give you a way to analyze semiconductor devices. So we'll initially start with the basic properties. We'll spend about 3 weeks understanding the basics of band formation, what are energy bands, what is doping, electrons, holes, and so on in semiconductors. So we will spend some time on that. I'll also introduce right up front in the first week itself, I'll talk about quantum mechanics, 1 or 2 lectures on basic foundations of quantum mechanics so that you understand how quantum mechanics is influencing semiconductor device operation. The reason I'm doing that is, if you look at the modern MOSFETs, they are quantum devices. They are in the scale of nanometers. And if you want to understand them, you need to know some elements of quantum mechanics. So I introduced that in the first week, and of course, develop these properties of semiconductor devices. So after that, we will move to PN junctions. PN junction is one of the simplest semiconductor devices. It is simply, you can take a P-type semiconductor and an N-type semiconductor, form a junction out of it. When you analyze that, you learn a lot of basic principles. We will spend 2 weeks doing this. And I'll also have some exercises on an online simulation tool called as NanoHub. It's a website that hosts a lot of interesting semiconductor device related material. So we'll also run some simulations on that to help understand how PN junctions operate. Okay. And then after that, I'll move to MOS capacitor. Now, we are all familiar with a simple parallel plate capacitor. You have two metal plates separated by an insulator. So we understand that, Q equal to CV and so on, right? But a MOS capacitor is slightly different. Instead of two metal plates, we'll have one metal plate and one semiconductor separated by an insulator. So how does that operate? So we'll spend 2 weeks understanding the operation of a MOS capacitor. What is, how does it respond? What is depletion, accumulation, inversion? What is the threshold voltage? How fast does it operate, and so on. So the reason we spend 2 weeks is that it is at the heart of a MOSFET, which comes later. So essentially, a MOSFET is an extension of a MOS capacitor. You can think of it like that. So we'll first finish MOS capacitor and then move to MOSFET. And then in MOSFETs, we will talk about the old, long channel devices, and then also talk about what are short channel effects. Because starting from the year 2000 or so, MOSFETs have been operating in a regime which we call a short channel regime. So we will talk about their IV characteristics, and we'll also talk about some metrics which are important in analyzing MOSFET circuits, be it a digital circuit or an analog circuit. What are the various metrics of a MOSFET that are important? Okay, we'll talk about that. And if you look at most of the semiconductor device books, you will see that the description ends somewhere in, I think, 2000s, I would say. They stop there because there's really no book that covers the most modern devices. So I'll spend one lecture on actually trying to give a glimpse of what happened since 2000 to the even 2020. what is the evolution in the MOSFETs in the last 20 years. I'll give you a lecture. It's a glimpse, but you will understand, based on the principles that you have learned in this course, you'll appreciate what is happening right now. Okay. So with that, I'll close the electronics part of the course. And then in the last 2 weeks, I will talk about optoelectronic devices. As I said, optoelectronic devices are, another, great revolution that has happened simultaneously with the electronic devices. So we will talk about how light interacts with semiconductors, because nowadays you see that we have solar cells, on our rooftops. We have LED lights in our homes, right? So basically, these are devices, semiconductor devices that are converting electricity to light in the case of an LED, or light to electricity in the case of a solar cell. They're very, very interesting devices. We would like to understand them. We will apply the same principles that we learned in the first, the electronics part, and then see how how electronics and optics are essentially similar. Okay, and then finally we'll also talk about lasers, semiconductor lasers, just the basic principles, so that you appreciate what is happening. Okay, so that is the whole goal of this course. There are various reference books. I'll pick up a lot of material from Semiconductor Device Fundamentals by RF Pierre. It's a great textbook for conceptual understanding. Okay, and then I'll also pick up some elements from Donald Neiman. It's a more modern version, I would say. But I must emphasize that you should not read the textbooks end to end. That is not really the necessary for you at this stage. In an introductory course, what you're essentially what is needed is to have understand concepts essentially. Okay, so I'll mention various sections that I'm using from the textbooks. You can go back and read those sections, but just focus on as much depth as it is covered in the course, because the textbooks definitely have much more information than what is necessary for an introductory course. Primary beneficiaries, the primary or intended beneficiaries are the students who are pursuing their undergraduate programs, be it as part of their BTech or BSc or an MSc program. So whoever is having semiconductor devices in their courses or in the curriculum, they'll really benefit from this course. And of course, it's also useful for faculty who are offering these courses in various colleges. It helps to develop the foundations. And if they're interested in pursuing research as an advanced research programs, definitely this will be a good foundation for research in semiconductors. And in the course, I will, in the assignments for the course, I'll also pick up some questions from the previous GATE examinations. So students who are interested in appearing for GATE examinations will also benefit from it. So they can see how various concepts are actually coming in the previous GATE examinations. So it will help them. And finally, there are no prerequisites for this course. I'll assume that you have math and physics at a 10+2 level, and I'll try to develop the necessary content from there. So I don't really expect you to know already. Okay. So if you are able to follow the lectures and the notes that you have and all that, so that should be sufficient for the purposes of this course. Okay. So with that, I would like to thank you once again for your interest in the introduction to semiconductor devices. I really find this subject very fascinating, and I enjoy offering this course every time. And I hope that you will also share my enthusiasm for semiconductor devices after you have finished this course. So with that, I would like to stop. Thank you very much for your attention. Have a great day. Bye.